Alright, so let's start off exactly where we left off. We start Salome, and now instead of loading the saved file, what I will do is that I will load the script, the latest script that I have saved, right? And where is it? It's in the CFD demo Salome files, and I did some modifications. I did some playing around, but we will continue exactly where we left off. So as you can see, the command has been executed, and when I go to shaper module, just like that, I have my entire model ready to go, with most of the things being parametric. Not most of the things, but a bunch of things. So if I change the blade length to, I don't know, something insane like 500, the domain automatically expands accordingly, right? So this is great. So let's reduce that size, make it a bit more reasonable, I guess, and remove the all of the things that you don't want to see on a screen, the planes, the sketches and stuff. So this is what we got. Now the next step is obviously meshing, right? We have got a CAD model. It can be controlled by a Python code. You don't need to open this software. You can just launch the script using Salome as the executor, and then you can export the entire thing. You can export the entire model as a step file or as whatever exports the Salome environment provides you. Now that's great, right? That's good. So how do we go forward, right? So how do we actually go ahead and do the meshing part? So first of all, we need to create the surfaces, right? Because right now all of these are different solids, and right now what we want is places where we will define our walls, where we will define our let's call them fluid domain. How do we actually name them, group them, those kind of things. So there are multiple ways to go about it. One is to just actually choose the solids, press control, choose all the solids, go to this thing, partition, say yes, and suddenly we have a single solid, but we have 3 partitions now. Alright, so this is great. So now, when if I just sort of turn this into a wireframe, alright, so if you look at that, what we have is a fan, the small cylinder, the big cylinder. Now what this is representing is the contact surfaces between whatever that fan solid was and whatever this cylinder solid was, and this cylinder is representing the contact surfaces between the insides of this larger cylinder, the fluid domain, and our rotating domain, right? So to make it a bit more intuitive, we will do it by a different approach. So let me just go ahead and delete the partition. We get our solids back. Then what I will do is that I will perform a cut. So I will select the shroud solid, I will perform a cut, I will choose what I want to cut out of it, I will choose the solid blade, and just like that I have something. This is a solid cylinder, right? So what happened here? If I just go ahead and change the transparency of this thing, oh, the blade is still inside, we didn't lose it. So what happened here is that this is the equivalent if you just somehow remove the volume of the fan from the cylinder, and now these are surfaces, and now you can say that, hey, this is the wall, right? So but one problem still remains, which is the fact that we just lost our smaller cylinder, and we still need to sort of cut that out of the larger cylinder. So how do we do that? Well, you can go to this menu and choose recover and choose the solid that you want to recover. So I got my cylinder back. So what I will do now is that I will cut this smaller cylinder from the larger cylinder. So simply do that, and just like that I have my fluid domain sort of ready, where like if I just select the transparency thing, and turn off the blade, you can see we have got a tiny little cylinder inside this big cylinder. So that's all good. So now how do we go forward to meshing part? Well, first of all, we will export it to Geom, because Geom has a bunch of features that we would like to use. Alright, so when I go to geom, after clicking the export to geom button, suddenly I have my solids here. Let's hide everything, let's turn this thing on, and let's see what we got. So we have this shroud solid, right, which has the cavity of a fan inside. Now let's create a group. Let's select faces. I want to create a group of faces. Let's name it AMI1. The reason I am naming it AMI1 is so that people who are following OpenFOAM tutorials of a rotating propeller or something like that, they have a easier time to follow it. So let's select this, add, select this as well, add, and select this and add. So now these faces will be part of this group, right, AMI1. Apply. This is done. Now what we will do is that we will hide this face. We will hide this face as well. We don't want it. Okay. Hide. Alright, so we have our fan. We want to name it wall. Why not? It's just easier to understand. Naming it wall, we can name it fan wall, or the fan surface, whatever. But then you will have to define the properties when you are doing the simulation in OpenFOAM or wherever, that this is a no slip boundary, and if you don't name them intuitively, then at least in a large simulation you can forget, okay, what is what. So that's why we're just going to name it wall, and so in order to keep things simple. So let's select everything, add everything. So there are a lot of faces here, and then just apply and close. So I've got wall now, and I've got AMI1, right? So I've got two things going on for me. Right now, these are two surfaces. So these are two, like, treat this as a single surface. Think of it as a single surface, and think of this as a single. This is also a single surface, right? So how do we mesh it? Now, first things first. When you're dealing with these kind of models, chances are that, I don't know, you designed it with very small features, and when you're doing the meshing, you realize that the computation time is way too high, or maybe there are broken faces somewhere. So can you deal with that? Well, Salome, the geomodel in Salome has a bunch of powerful tools. So like, you can glue faces, you can sew faces, you can sort of so if I want to, like, reduce the overall tolerance to something like this, I can select this thing, and I can say apply, and what that has done is that it has resulted in whatever shape that gets generated if you remove those low tolerances. So let's see, if I just hide it, I don't know if something will be visible or not, because this shape is valid. So let's say you look at that. So it looks kind of similar, but maybe it removed. If it would have removed something, it would have shown us a notice, okay, this many faces got removed and things like that. But right now this is not required, I guess. You can actually check if your shape is reasonable or not. If I just turn the wall on, the fan on, and you can say, you can go to check shape, and you can say, okay, this shape seems to be valid. So Salome is saying, all right, this is all right, dude, I don't see any problem with it. So that's cool. But if there can be a case that something is broken, or a face is free, or is some edges is going out, something like that. So those things can happen, and you can there are enough tools here to sort of take care of that situation. So all right, so the next part is meshing, right? So how do we go about that? Well, again, you can just sort of go to the mesh module, and we already have shaper results ready to go, we have geometry ready to go. So what do? I can select this shroud solid, right, and I can directly sort of create a geometry from here, and and the meshing happens from like 0 to 3. So first dimension, 1 dimension, 2 dimensions, 3 dimensions. So it proceeds from this way. So like, if you define some parameters for the 1D discretization, sorry. So if you define the parameters for 1D discretization, those same parameters will then be used for the 2D, and then will also be used in the 3D, but you can have different algorithms. So you have all sorts of different algorithms on how you actually want to go about dividing the domain. But instead of just directly clicking on create mesh and choosing some parameters, what I will do, what is a good idea, is to use some meshes. Like they already in the help panel, they can say use local sizes and use some meshes. That way, like you focus on the areas where good mesh is required, and like so that like if you do the meshing in general, if you do the meshing in a one go, chances are that the parts where you need a good mesh don't have a good mesh, and there are places where mesh is too small, or places where the mesh is too big. You don't have much control over things. Using some meshes and using local sizes and stuff will give you more control on how your mesh looks, and in general like will give you more control on the speed of the simulation, because if your mesh is good, the simulation will be faster. But if you have a bunch of nodes that are really small, and your computer is pulling double precision for those things where you actually don't need any accurate data, then that is not efficient. So how do we do that? Well, what you can do is that we can go and we can create a mesh, right? But instead of 2D, we will only select the 2D option. We'll go to 1D, and let's choose wire discretization. Let's define it to be I don't know, let's see, which should we choose. Let's choose adaptive, right? So minimum size is quite large, we don't need that large. We will reduce it to 0.1, and we'll change it to 20 or something, right? And again, we can use the NetGen 2D algorithm, and we can decide from the NetGen 2D parameters. Like again, let's make it 20, make it 0.5. What was the? Actually, I forgot what it was. Let's see. It's just 0.1. Let's make it 0.1 as well. All right. So okay, apply and close. So we have a mesh here, and now what I can do is that I can create a sum mesh, right? In the mesh, I'm creating a sum mesh. The geometry that I want to create a sum mesh on is on the wall, and now I can define like the fan itself. There are places where I would really like some accuracy to be there. So what I can do is that when I'm doing this instead of this adaptive one, what I can say is that okay, the minimum size is 0.1, say, but the max size is only 5. You don't get to go bigger than that, right? For the specifically for the fan part, and again for the NetGen 2D, again we do something similar. We say, hey, you get to be 0.1 at the minimum places, but you don't get to go above 5. Let fine SCB. We can go ahead and choose course, so to make the computation a bit faster, because this is not like in general, we're not going to use it for actual sort of practical purposes, so that's fine. Apply and close, and at this point you can sort of go and say okay, compute mesh. Alright, so let's wait for it to get done. Because we were so lenient with our meshing, and in general the parameters that we choose, this is fast enough. But if you were really going for something, if you were designing a fine mesh, chances are that this can take a lot of time. It really depends on your processor. So if you want to do fast meshing, what you should do is that you should get a processor with high core count and high boost frequencies. Now like okay, something is there. This is interesting, you know but what about the fan? I can't see the fan, so how do I see the fan? Well, let's hide it all, and let's see this one. Okay, so it took some time, but hey, we have our fan mesh here, right? Not the greatest mesh I've created, but it's fine for this discussion. It's actually more than fine if you actually think about it. the how CFD was done in the early stages, where you would model something like a car with a very simple model. You wouldn't model things like the side mirrors and stuff. So um, this would still get you in the ballpark of how this fan would perform. But yeah, there's definitely a lot of room for improvement in general with this thing, uh, but we are going to completely uh, avoid that today, and like if you want to see, okay, what is the other mesh, like the shroud, what we can do is that we can create a clip. So there's something called clipping. If we look here, we don't have any plane right now. We'll create a new plane. It's where is this plane? Okay, this is a weight plane. I don't want that. I want something that's 0, 0, 0, and it's let's say YZ ZX. Okay, I don't know what happened here. Absolute Z ZY. All right. So let's see what we have got here. If I rotate here, you can see the internal cuts, right? Now, as I said, this is not the greatest mesh around. The element sizes here are too big, so it looks a bit bad. There are these edges. This part is also not great, but we'll discuss that later on. How we will perhaps have a dedicated series to discuss how to actually achieve good meshing and stuff. But for now, you look at this and you get the idea on how do we get the meshing done when you're dealing with this sort of parametric modeling. Now, continuing with the theme of keeping things easily controllable through code, what I'm going to do is that I'm going to save it. So remember that so what has happened is, the reason it's asking me to save again is because I loaded it through script. I didn't load the parametric.hdf file. So let's call it .hdf, right? So that works. Now again, going back to that dump study portion, right? I will name it pmspd mesh dot, right? So that saves it. Now, like if I just go back and go to Salome, if I go to CFD demo and Salome demo, and if I just go to pmfspd mesh.py, see, we do not only have the code to generate the CAD model, but look at that, now we also have the code to generate the mesh. And exactly as earlier, you can actually play around with the variables now. You can see, those things, the parameters for the meshing and stuff are also defined through very simple Python functions, so you can change them around. So you can completely automate the process from the CAD model to the meshing part just using simple Python code. And later on we will see how you can go even further and completely design a pipeline that not only goes from CAD to meshing, but also goes from CAD to CFD solver, and you can design a pipe. So if you work with a lot of fans, say, if you are a fan engineer maybe, and that's all you do, you can create a pipeline and you can store different scripts for different situations, and you can basically just write in the kind of parameters that you want. The code will run, automatically optimize some base design, and get the results that you want, right? So that will be, so for now we will just close the discussion here, right? And from in the next discussion we will sort of go over our mesh again, see if there are things that we can improve. We will also mesh the volume inside. We haven't meshed the volume inside yet, it's just the surfaces. So after that, when we are done with meshing that, we will also mesh the larger cylinder, the larger domain solid, and after that we will use some sort of solver. Yeah, you can use OpenFOAM, you can use DCFD, you can use Flow 360, but I would like to keep the discussion a bit general and easy to understand. So we'll see, how you can actually connect this to any sort of CFD solver, right? Again, the idea here is that you can export to whatever format that fits. So CGNS is a popular format that a lot of proprietary softwares use. STL works, UNV you can use for your OpenFOAM. So a bunch of formats are there, right? And even in the meshing, if you saw in the meshing option, like if you when you create a mesh, you also have things like GMSH. So all of these things are related. You can sort of plug and play with these things. It doesn't matter. So I did this thing with Salome. You could have had something like FreeCAD where you did the parametric modeling. Then you could have had something like GMSH do the meshing for you, and then you could have had any XYZ solver which has an API that you can connect to, like if the code is entirely proprietary. So I don't know how you would do that, but at least for the open source pieces of code or the softwares, even the commercial softwares like TCFD give you a lot of freedom to play around with their code and mess around. So even with them you can easily create a pipeline that directly connects from all the way from your CAD geometry to your CFD solver. So that's about it for now. I will get back to you guys with the other tutorial that will maybe 2 more videos, and then we will be done with our entire simulation. Thank you.